Good afternoon, everyone, and welcome to this webinar held by CONSELF. I am Ruggero Poletto, and I am talking on behalf of the whole company, and I am very happy to have this short presentation with you. The topic of the webinar is going to be HVAC, thus ventilation, in particular CO extraction from parking lots. We know that in Europe, many countries are actually emanating rules about ventilation on these particular tools, in particular for fire prevention. And in here, we are going to see how some modern tools like CFD can help engineers and designers dealing with them. This is part of a series of webinars which are going to be throughout the whole month of April and the beginning of May. The webinars are going to refer to some of the most common applications of CFD, such as valve flow, hydraulics pumps, wind tunnels, and building. In here, you can actually see the dates. First of all, let's start our presentation with a brief description of the company. We started out last year in April 2015, and we have now our headquarters in Milan, in Viale Forlanini 23, and we also have some operative locations throughout Italy. At the same time, we are creating our distributors network worldwide. In particular, we are currently present in 3 countries, such as Croatia, South Korea, and China. Do not hesitate to contact us at the following links or email addresses in order to know even more how to get in touch. What we do, we have 3 different types of services. The first one consists in a CFD on the cloud application available through the website app.conself.com. The application, which is available 24/7, is accessible directly from your own browser without installing anything on your local machine. In this way, you can use our remote server to take advantage of the power of CFD in multiple fields. Another service we have just started is the cloud computing one, in which we allow users to access our huge computing power in order to run their own software, or the most popular ones, such as Open Cascade, CONSELF, Fire Dynamics Simulator, FDS, and so on and so forth. In this way, once again, we use a pay-per-use methodology in order to charge just for what you use. Last but not least, we have an engineering consulting activities in which we offer our technical guys and our engineers to help you designing, in particular, optimizing the geometries in order to achieve higher efficiencies of the products, lower level of noise, and in general, a better design, also according to the current European regulations. Let's have a quick look at the tutorial we're going to go through together in a little bit. This is a drawing of the car park we are going to simulate by using our CFD online service. As you can see, the car parks is made up with a certain number of car park lots, garages, and there is a window to access open air. Remember, this car park is indoor, it's built under the earth level. In this way, we have to build a window on top, on the roof of the car park. And there is a ramp access to get in or out of the car park with your car. Inside of the car park, there is a small jet fans, this little cylinder over here. This jet fans has the goal to convey the air from the open window to the ramp outlet. So in case of fire, it allows the air to get, and the smoke and the heat produced by the fire to get out of the car park. And in this way, it gives a certain level of safety. I am referring now to some part of the European regulation in fire safety engineers, in particular to the recent Italian regulation that was issued on August the 3rd, 2015. In this regulation, the Italian fire brigades decided that it's on the responsibility of the designer the decision to use this type of instruments. So for the first time, CFD instruments are allowed to be used in the regulation, not as it used to be before. At the same time, the fire brigades said that some procedures to follow in order to decide where the fire has to be settled, and at the same time, what is the magnitude of fire, in particular in terms of heat release rate, so the release of heat from the fire, so the increase of temperature of the whole car park. In section M2.6, the prescribed heat release rate has to be at least 5 megawatts. This is, according to the regulation, the heat release rate of a single burning car. At the same time, the same regulation prescribes a certain level of CO and other particulate to be emanated from the fire in case of a fire event. This has to be at least 0.1 kilos of particulate for each kilos of burning substances. In this way, we are able also to consider during the simulation the diffusion of pollutants created from the fire, and we are also able to prevent and maintain for a certain number of minutes, a certain amount of time, the whole car park safe for the people to evacuate, but also for the fire brigade to get in the car park and save some more souls. Let's move then to the simulation and let's see what I am saying, but from a practical point of view. So 1 second, I'll have to change the screen. Okay. Here it is. This is a normal browser. I use Google Chrome, and I am now on CONSELF website at the web address conself.com. You can see that in here there are the most relevant information for you to use the software, but what is important to notice is that to access the application, you don't have to install anything on your local computer. You just have to type login and access by using your own user and password. As you can see in here, I have already inserted my user and password, and I can access the software, the platform. Here it is. So I am now in the platform, and this, whether you believe it or not, is a full CFD software. You have a huge amount of hardware resources in background for you to run and to use. The biggest news in the recent release of CONSELF web application is the introduction of what we call application. These are a number of tools which allow us to run specific type of CFD simulations. In particular, we have a general application in which you can also run heat transfers, calculations, an oil and gas application which is focused on calculation of particulate flow with particles. Then we have the HVAC jet fans application, which is the one we're going to see in this tutorial. And we also have a turbo application for single reference frame pumps. The other applications are going to be described during some other webinars later on. So if you are curious, I suggest you to register to those. So I just create this new jet fan tutorial, and I use the HVAC jet fans web application. Sorry, I did it wrong. Jet fan tutorial. I type create, and I get into the geometry phase of the simulation. The software and the platform is organized to guide the user through a certain number of steps, which are the most relevant steps you have to go through in order to run a complete CFD simulation. These steps are geometry, mesh 2D, mesh 3D, then there is obviously the CFD and the results. So let's start by uploading the geometry. 1 second, I need to find it. Here it is, car park step file. So we can open it. It takes a few moments for the application to load the geometry file, but if you manage to do it successfully, you'll see the step file on this right-hand side window, which is our brand new CAD file visualizer. Okay. In here, we can handle the geometry and select the boundaries which have to be defined in order to run the simulations. So let's start by selecting the first boundary, is this red zone over here, and we create a ramp boundary. As you can see, as I finish selecting one boundary and applying and grouping it, basically it gets dark gray, okay, in order to say, hey, I am selected and I have already some details on me. Having done that, we do the window in here on the top, as we saw in the picture earlier. So window, and we create it. And then we create a top, ceiling, and bottom floor boundary. We call it floors. Okay, now we want to get inside of the car park. In order to visualize the car, the schematic car we put inside, and the fan, the fan we put inside of it. So by clicking on selection, we can hide all the boundaries selected. They disappeared, as you can see. We don't have ceiling, we don't have floor anymore, and now we have this, which is the simple sketch of a car we put inside, and this, which is the fan. So let's start from the fan. We select this circle surface over here, which is the jet fan pressure zone. The area of the jet fan, the air moves in that direction, so the air is sucked from this side and pushed toward the ramp. So this is the pressure side, and this is the depressurized side, this red on the opposite side of the fan. So jet fan depth to mention the pressure. Okay, last but not least, we select the top surface of the car and we call it car. This surface is important because later on we are going to prescribe some fire boundary condition on it, okay, and we use that for this reason. So we can hide the boundaries we have just defined, so there is no more top surface over here. We now want to merge all the other boundaries into a wall, which is everything that remains. So once again, selection, we select all the boundaries, we create a wall boundary. We type on create, and that's it. So we show all the boundaries, and let's see, everything is dark gray, so everything has been correctly defined. By clicking on Manage Boundaries, you can access this particular table, which actually shows you in a more clear way how you defined the boundaries. It is possible to edit the name by double-clicking, to show or hide some part of them or all of them by clicking on Show and Hide buttons. Well, we have now to define the geometry, the units, the file units we use in the file. In order to decide them correctly, we put this small icon over here. This returns us a value in Z of 750 units. So it's like if it is saying the car park from the bottom surface to the top window is 750 units high. So I can understand the units is in centimeters because the car park is 7 meters 50 high. We move next and we move to the internal flow type. And now we can submit the simulation. We confirm the submission, and here it is. The process is currently running background in our application. We can see it with this progress bar. It's worthwhile mentioning that when you register to any plan available in CONSELF e-commerce, in CONSELF website, you are gonna be given a certain number of credits. Every credit represents 1 hour of this background process running. So every time you submit a process and every time you see a case bar in progress, you are going to be charged some credits, but there is no charge during the setup phase. So when I open and I select the boundaries and that phase, there is no charge at all for that. So the geometry phase is finished. And everything is correct. In fact, we are now in the Mesh 2D phase. So we link to the previous geometry. Once again, we have the car park, but this time, as you can see, the surfaces are grouped exactly according to the definition I gave before. It is now time to define a certain level of 2D mesh refinement for each surface. In fact, the goal of this step is the definition of a triangular mesh on the surface of the car park. So in the ramp, which is this one, if I select here, I can actually visualize this is the ramp. If you see on the top right side of the CAD visualizer, you can actually visualize the name of the boundary. So I select the ramp and I select the standard size, which is 0.1 meters, 10 centimeters. The default values are prescribed correctly for everywhere in the car parks. I just want to increase the refinement of the jet fan area. So I just put 0.025 meters, 2.5 centimeters. This is the dimension of the triangles which are going to characterize these entities. And I'm also increase the refinement to 0.05 centimeters close to the car. This because I want to be able to correctly reconstruct the car fire situation. Once again, I can submit the process. I confirm the submission, and here it is. Now the process goes back in background, and it's running while we can do anything we want. We can also log out of the web application of this website. I just go back a little bit to what I said before about the credits. I said that only cases which are in background actually uses credits, while all the geometry and the simulation setups are for free, basically. Well, in the dashboard, you have quite a few statistics about the way you are using your credits. In fact, there is this pie chart returns the number of credits available and remained to use. And there is also in here, we can't see it very well, but it's an orange slice which returns the number of credits which has been used. On the right hand side, instead, we have the number of credits used per single application. So in our jet fan tooth, I've used so far 1 single credit. In another tutorial I did this morning, I used 5 credits. In this way, we can actually have feedbacks on the number of credits I'm using to run the simulation, and then it's very useful to know what are the actual expenses. Let's move back to the simulation. As you can see, the progress bar moved forward. Now we are at 40%. And there is also an ETA, so estimated time to finish is 1 hour and 5 minutes right now. Hopefully it should be shorter than that. Usually the step that requires the highest number or the highest time is the CFD phase, because we have to run that for several hundreds, if not several thousands iteration or time steps. For this reason, in the present tutorial, we're gonna skip a little bit that phase, and we're gonna have a look at the results I ran previously in a previous CFD simulation. Let's wait a few more seconds. Here it is. Finished, so we can open the case once again. Everything finished successfully, and we are now in Mesh 3D. In this phase, we are building the mesh inside, the volume mesh, the elements inside of the car park. Probably it's worth a while mentioning why we are doing all of this. Well, we have to keep in mind that the CFD simulation resolves flow equations, and in order to resolve them, it is compulsory to have a certain number of elements, which are used as elements to be based the solution on. All right, so this is the reason why we are differentiating the mesh in this way, and we are dividing the geometry in such type of elements. In here we have hexahedral type of mesh. So this mesh type consists of cubes. We define the dimension of the cubes, but before doing that, let's have a closer look at what we are doing by using our CONSELF manual. The user manual you have available here at the bottom left of your screen. I hope you're still able to see and to see what I'm doing. I think so. So if we move to Mesh 3D, we have a preview of the hexahedral mesh. This is what we are building right now. So we have a certain number of cubes with a certain size, and we have smaller cubes closer to the object inside of the mesh. So we have to prescribe a dimension, a standard dimension of the cubes, but also dimensions for elements approach closer to the surfaces we defined previously. Okay, so for these reasons, we define here 0.25 meters. This is the standard dimensions of the cubes. And in this boundary treatment section, we defined particular cube dimensions for each boundary. So we define 5 layers of cubes with 15 centimeters dimensions. In the window, once again, 5 layers of cube with a dimension of 15 centimeters. On the floors, we just leave the default value of 0.25. On the jet fans, we just apply 5 layers of cell with a prescribed size of 2.5 centimeters. So we want a higher refinement on the jet fan, so pressure, but also on the other side of the jet fan. So once again, I use the same values. Let's move on the car. Once again, 5 levels, and this time I want the refinement to be 5 centimeters. So refined, but not as much as on the fan. Last, the wall, on which we apply the default value of 0.25. So let's push submit. I confirm I am sure, and suddenly the process runs in background with this mesh 3D phase. This time it should be quite quick to run the mesh, but obviously it is very, very important, I would say fundamental for any user to do and try the mesh again and again. Remember that the element size prescribes somehow the accuracy we are going to get from our CFD setup. So I suggest every time to run a very coarse mesh just to see the general feature of the flow, and then to run a more accurate mesh where we reduce the refinement level of those cells where we have high velocity and pressure gradient. As we see while I am talking, the simulation moved on. Now we are at 70% of the progress, and the estimated time is 25 minutes. Let's wait some more. We should get to the conclusion of this meshing phase relatively quickly. It shouldn't take that long. Meanwhile, I would like to mention the support availability from our web application. Because of the nature of this, since we are on a browser, everything, including the support, is real time. So you can actually click on contact support in order to identify your question, define the type of issue you are running through, and by following this procedure, you are in contact with our support team. It's worthwhile mentioning also that this is a cloud application, and thus at the beginning of the simulation, you notice that I uploaded my geometry file to CONSELF server. Well, this file actually is stored in our server, and CONSELF will never publicly publicly release that file. We act like a consultant, so your privacy is actually saved. Also considering the privacy tools, the certificate of privacy released by Komodo, we have to certify our safety. At the same time, we continuously use feedbacks from users to keep improving our web applications. And just to mention some new features which are going to be released relatively soon, there is going to be a mechanical solver for static analysis. So stay in touch for all these news, not just for jet fans. Well, the meshing phase is taking a little bit longer than expected. So let's wait a few more seconds. Otherwise, we can actually see a case I previously ran for you and investigate and see the CFD setup through that phase. I once again want to repeat that it's not compulsory to be logged in the application while the process runs in background. I could close this window and I could move somewhere else. I could also turn off my PC. It's also another nice feature is that the whole application is available from any internet connected device. So you don't need actually to carry on your computer with anything installed on it. Basically, you can use also your mobile phone, but I rather suggest you use a tablet or any mobile PC or any PC you may use accidentally also everywhere in the world. The only requirement is to have a internet connections, obviously. At the same time, most of the graphical rendering is run also on the browser, so it's not required even from the graphical point of view to have anything. Okay, a few more seconds. We are still at 70%, but in order not to take too long of your precious time, I would rather move to something I did previously, another tutorial I ran previously. It's once again the jet fans tutorial. In this way I am able to show you the mesh I did in another case I ran previously. This is the usual car park we saw so far. So we can visualize the mesh by clicking Surface with Edge, by applying it. Okay, this is the mesh. We can actually see the uniform level of cells all over the car park. The higher refinement closer to the inlet ramp and closer to the outlet window. But also we can see the higher level of refinement around the fan. This is the location of the fan inside of the car park. So it's another very, very useful part, and where precision is very important. As you can see in here, we have two types of models. One is for CO extraction calculation, and the other one is used for a fire scenario. For timing reason, we are going to just see the CO extraction, but I do invite you to make questions also about the fire scenario. Turbulence model, I'm going to select as Falar-Talmaras. The default fluid properties value and pressure and velocities are referring to standard environmental settings, so air at 15 degrees. Obviously, you can modify them by yourself, but most of the time you can be happy with the default values. We can move now to the definition of the boundary condition. So in here, we have to specify where the air comes from, where the air goes, what is produced by the fire in the car, and so on and so forth. So we specify the ramp is this area over here. We specify it as an outlet. We have the window. Obviously, the window is one outlet. We have the car surface, which, as we said before, we want from the car to produce some CO. So we want some pollutant to be produced by the car to check how our extraction system can handle with that. This is the value of CO produced in kilograms per second or over square meters. And this value refers to a single car production, so we can leave it. Otherwise, if you have a higher number of cars, you just have to multiply that by the number of cars you have available. Then we have the jet fans. On this, we have to specify the velocity on which the jet fan pushes the air, or on the jet fan suction, we have to specify the velocity at which the jet fan sucks the air. We use a negative value to say this velocity is sucked rather than pushed. On the floors, we specified a standard wall no-slip boundary value, and the same for the wall. So we did all the boundaries in a few seconds. Yeah, we have to specify the steady flow solution, which is the only one we have available, the number of iteration, which is 100, and to save iterations every 25 time step. As I said before, it's very important to use a very high number of iteration. 100 is the least number of iteration we can use, but as CONSELF, we suggest to use a several number of thousand, like 2,000 or 3,000 iterations, in order to be sure you achieved a correct level of convergence. We submit the job, and here it is. The job runs in background. We have this job running in background, and step by step we will see the progress bar moving on, saying that the CFD simulation has started and is currently running. As we said, as we can see, the tutorial we did before finished. So actually, the 3D mesh has been generated for that one. But we are gonna now see the results I did previously for you. So I opened another case on which the CFD has been completely performed. Here it is. Okay. In here, it is possible to do 2 or 3 things very important. First of all, it is possible to see the residual levels. As we can see, they decreased, but they are still quite high. So 0.2 for the pressure, if I'm not wrong. So probably, if I had to be honest, this solution has not arrived to any convergence, totally convergence. So I would restart it with a higher number of iterations. And at the same time, it is possible to download the results on your local machine for you to post-process with the most popular post-processing tools such as ParaView, Insight, TechPlot, and so on and so forth. At the same time, CONSELF gives you some capabilities, post-processing capabilities directly online. And we use now them in order to visualize the CO inside of the car park, the CO concentration. So I just specify the slice. I specify I want to see the CO. So here it is. We move to the latest time step. And this is the CO level. Very often, in order to have an improved graphical rendering, I am used to put a transparent layout of the whole car park. In this way, we can understand more correctly where we are. As we can see, this is the CO concentration. The car is around this area, and we can see that the airflow from the jet fans actually pushes the CO towards the exit. This is the CO level. It's in kilos, so it is possible to obtain the famous part per million by dividing by the air density and multiplying it by 1 million. But I also want to see the velocity contour of the car park, so I select the velocity, I click apply, and here it is. This is the velocity development around the car park. We can actually see that since our jet fans is about here, we have this red area, which means there is quite a strong push in velocity flow. Obviously, it is also possible to capture an image from our web application and right-click on here and click Save Image As in order to save it on our local computer. All right, I'll just move back because also the CFD we run has finished. So as you can see, it took us just 40 minutes to do not only the simulation, but the whole webinar. So we can move on with the presentation, which now goes to the question and answer moment, which is probably the most important part of the presentation. I invite you to make any question. You can actually see the instructions to make questions. You have to click on the icon on the top right, you can see on the top right, and then click on question and answers. In this way, I will be able to see your questions and to reply it. Please don't hesitate to make questions. I am available now for a few minutes to any of you. Here it is. There is the first question is about the service, the level of the service, and the pricing. Well, CONSELF gives you this continuous service, so there is no limit, like it's not suspending during nights. So you can access it every time, night and day. And we have multiple plans available online. The easiest one for you is the free plan, which gives you 20 credits per month to use for your simulations. And then we have payments plans, 200 euro per month. You can run up to 5 simulations. Or if you want even more, you can pay 1,000 per month and run about 20 simulations per month. All the plans are available to any users, so you can activate or deactivate them by yourself and take advantage freely. At the same time, for companies and wide users, we have offline plans which have to be assessed directly through us or through our distributors worldwide. Okay, another question about the documentation. As I said before, I would like to invite you to see the documentation which is available online directly through the platform. It is possible to take advantage of all the tricks we put online, and to check out also some default values for the parameters like the mesh sizes, Y+, or even some more advanced parameters. Okay, another question, it is probably about advanced parameters. Uh, it is possible to select the convergence criteria, like the level of convergence. Well, for the moment, it's our decision not to make it possible. By default, the convergence criteria is selected by the software according to the application. You just have to specify the number of iterations. This is for your safety in general, because in particular, unexperienced user may select a low level of convergence. And in general, I can say this convergence criteria is never below 10 to the power of -4. So it's quite a strict level of convergence. At the same time, we have to keep in mind that we have also transient solvers available online, for which we don't provide, and obviously it's not calculated either, any convergence criteria. For those, there is another criteria on the time step. Once again, the user only selects the maximum time step to be allowed, but it is on the software the calculation of the current time step according to the stability we want to provide to the solution. I'll wait for some more question. Here it is. There is one more. It is about the cloud nature of the web application. I confirm, as I said before, that it is possible to log out of the application, to shut down the PC, and to move to some other tasks while the simulation runs in background. So it is not compulsory to being logged in to keep your PC on. Another more technical question, it is about the models availability. Well, turbulence models available in general are laminar flow, which is obviously not a turbulence model. We also have K epsilon, K omega SST, and spiral timeless. You may not find all of them, but some of them may be filtered out according to the application you are using. So pay attention to it. We are also thinking about inserting some large eddy simulation models, but we are considering that for transient simulations only, obviously, and some more advanced features are required for those to be used properly, such as field averaging, etc. It's worth a while about the models mentioning that the boundary conditions available keeps being increased day by day. So for the moment, we have velocity. In general, they are classified into 4 groups: inlet, outlet, symmetry, and periodicity. And it is possible to select these boundary conditions freely, basically. We have another question about initial conditions. For the moment, it is possible just to initialize the flow in a uniform way all over the mesh. So assign a single value all over the mesh. Obviously, we have in our roadmap to initialize the flow from a coarse mesh solution to a final one. This actually is another interesting feature together with some other we have in our mind for the future. So I suggest to subscribe to our newsletter to stay in tune with some more tools we have in mind and some more advancements which are going to be released in short time. I'll wait a few more seconds for some latest questions. What I want to mention, meanwhile, is that CONSELF is online on the most common and popular social networks, such as LinkedIn, Twitter, Facebook. It's worthwhile mentioning YouTube. We are gonna release the record of the current webinar on YouTube, which is gonna be available right after the presentation. So if you missed the presentation or you want to share it with some of your friends, feel free to do it. I also want to invite you to email us. You have the contact info@conself.com is our standard email address. There is another question who has just arrived. Can you import external mesh files? For the moment, not yet. In general, what is worthwhile mentioning is that we have a mesh file converter for OpenFOAM available in our e-commerce. So I don't say it won't be in future, but it depends on the requests we get from this point of view. We can surely talk about the mesh format. As you may know, there are many mesh formats available, such as UNV, Fluent, and some more. But in general, here in CONSELF, we like standard file formats. So if we and when we implement this feature, it will be in CGNS file format. Okay, I don't see any other question, so I really thank you all for taking part to the present webinar. I hope you liked it and you actually followed it with some positive ideas and opinions. I really thank all the people who took part to the questions and answers phase. It was a very positive, I think, contribution from all of you. So I consider this presentation over, and I'm looking forward to welcome to our web application. See you later. Oh, before saying goodbye, there is one last question I managed to read before closing the broadcast. It is about the cloud computing service. As I said before, we, because of the CFD on cloud, we offer this type of service, so you can access via shell or also via remote desktop our server, in which you basically specify to us the number of processors, the number and the softwares to be installed, the size of the RAM, of the memory RAM you want to be available. And in this way, you have this machine available to you and to your needs. This machine will be available through internet, so something like name.conself.com. You can access it and run your own applications or any other we can provide. There is a list of the applications available. It's on our website. You just have to go under the services menu, and you will click on cloud computing service. The most popular application we use so far are Fire Dynamic Simulator. There is OpenFOAM. There is some more about simulation like CodeAster or CodeSaturn. We also have some graphical rendering application, or we can also install third-party applications. So you can provide us the application you want. Or also, I don't know, it is also possible to use that as a database server or many other things you want. This service, once again, is paid per use. So at the end of the month, you'll receive an invoice which takes into account the number of computer according to the CPU resources you used during the month, and you'll be charged just for the resources you actually used. I hope I replied clearly to most of the questions. I really thank also this latest questions, which was probably I didn't speak too much in details about this type of service, but it was a good question and a good point. All right, I'm not receiving any more questions. So once again, thanks to you all for being part to this webinar. And I hope to see you and to interact with you throughout our socials. See you, bye.